Hi everyone, welcome back to workshop, and it's repair time again. And I have to admit right off the bat, I have so been looking forward to this unit arriving. It's a Keithley 2001 multimeter. It's a 7.5 digit multimeter. And they don't come up very often. I spotted this one for sale. I lowballed the owner and it was accepted. So it's just arrived in the workshop today, and I can't wait to get inside it and to have a look around and see what sort of condition it's in and do some checks before we actually go and power it up. Now, the ad did say that there was nothing on the display, and that's all it said. So there could be any manner of problems with it. So let's get it down onto the workbench here and let's get the cover off and let's take a look inside. Now, as you know, Keithley's now part of Tektronix, but when Keithley first came out with this unit, I think it was back in the early 90s. They're still available for sale today. Farnell are selling them for £6,600 UK pounds at the moment, so they're an expensive multimeter. It's not surprising given its reputation and the fact it's a 7.5 digit multimeter. So let's get the lid off. So I'm presuming this particular meter was used in a workshop setting. That's because it's got this sticker along the top here, differential voltmeter. So probably this meter was used for a single purpose, maybe in some part of some production line or something like that. And all it did was some differential voltage readings, something like that. It looks pretty clean inside. Of course, it does have this cover, so we'll need to get that removed and take a look underneath. And on the other side, you got the CPU board. Again, very, very clean. Now, there is a fan inside it, but it is extremely small, so you're not going to get that much dust inside it. But everything looks absolutely brand new on this side anyway. Yep. And on this side here, we've got the transformer and the power supply circuit here. So let's get this cover off and take a look underneath. Now, I've done a bit of research on these units here, and everyone that's repaired one so far has reiterated over and over, don't power it up until some specific checks have been made, and that's the power supply circuit. Basically, there's a bunch of electrolytic capacitors inside these units, and they notoriously go bad and corrode the board. And if you don't sort out the power supply first, you can basically destroy the rest of the circuitry. So that's what I'm going to do first. Now, to get this cover off, I will need to remove this ferrite core here, so I'll just be careful prizing that out. Don't think I need to take it right out, just get it near the top, enough so that I can prise the cover free. There we go. Let's take a look inside. So here we are for a good look inside at the analog board, and here are all the electrolytic capacitors that I'll need to change out no matter what I do. So I will be making a list and getting those in order from RS, getting them ordered as soon as possible. But looking down onto the PCB, in and around, in between the actual electrolytics, I'm not seeing any corrosion or leakage at all on any of those caps, and there's no bulging at all either. So whether they've been changed out prior, not really sure. This one here is at a funny angle, so it doesn't look like it's been inserted properly, but I guess once I get the board out and take a look at the other side, maybe there'll be some flux residue if those caps have been changed. But in saying that, I will be changing them anyway. And at the same time, I'll order up a fuse holder for this rear panel fuse here. Looks to be a standard size, so I should be able to get one of them. But wait a minute, before I go and order the new fuse cap, I think I'll need the whole new fuse holder, because I thought that was a little wee groove in the fuse holder for the catch, but it's not. It's a cracked housing on that fuse holder. Oh, yep, I just pressed it there and it basically broke to one side. And luckily I recognise the make that's got Fab written on it, so that's a shorter Fab fuse holder, so I'll need to go and order the whole thing and hopefully I can get them. I was just having a little browse around and I've spotted something already. So over here we've got the A to D converter board, so I'm just going to remove that because I've spotted something underneath that I think requires a little bit of a look. Let's get it out. And I think it just unplugs. There we go. So that's the A to D converter board, I believe. And look down here. Let me zoom in on that. Somebody has had a go at trying to replace or resolder an LM339. That's a quad comparator. Wow, what a mess. Hopefully there's no traces on the board being lifted, but yeah, I think I'll pull that from the board for sure and replace it with a new one and have a good inspection of the traces in and around that comparator. And the other thing I've spotted whilst I'm down here is that we've got a few test points there for, looks like, the plus and minus 8 volt, plus and minus 15 volt and plus 5 volt supplies. Probably for this particular part of the circuit to do with the A to D converter. So that's handy for measuring that. You know, I think, like I said earlier, I don't know anything about the Keithleys. You know, I've done a lot of repairs on HP and Agilent products, but I've never repaired a Keithley. So this unit and this system it's built around is completely new to me. But yes, we will be replacing that comparator there. So taking a look at the schematic, I've found the comparator in question, U316. There's 1, 2, 3, and the other one is over here. And you've got a bunch of flip-flops here and shift registers. So not too sure what they are doing without studying the schematic a little bit more, but it's just a comparator, so it's easy to diagnose, easy to measure once I get it up and running, perhaps, and then I can get the scope on it and do a bit of probing around. Yeah, but really that is a little bit of a dog's breakfast there. Absolutely, for sure. But round about it, nothing looks blown, nothing else looks like it's a problem. Doesn't look there's been any other joints that have been resoldered or ICs or anything replaced, so hopefully it's just local to this IC here. What exactly the symptom was on the actual meter, not too sure, but I'm sure we'll come to that. And before I start ripping it apart, I really wanted to find out the age of this 2001, and I thought I would get that off the PCB. Over here on the right hand side, let's zoom in there, we've got some numbers. 9821-4, could that be the 21st of April 1998? Well, I don't think so. I think the unit's a good bit newer than that, and the reason I'm thinking that is I think this is the second generation board. Therefore I think it's a B class model rather than an A class model. And taking a little bit of a closer look at some of the ICs, we've got some date codes. 0552, 52nd week 05, we've got more down here on this analog devices chip. 0544, so 44th week 05. And if I turn the unit over, here we are looking at the digital board. Again, we've got some date codes on the RAM chip itself. Is that 1106? And importantly, we've got the ROMs here, the firmware B16, and I believe that's the latest ROM. And I tried to find out when B16 came out, and I've come across a roundabout way of figuring that out. So over on the XDev site, I found a firmware upgrade note, a release note for the 2001, and it describes an upgrade to fix a problem to do with average responding RMS, I presume. But if we look at page 2 of that there, it mentions the B16 firmware. Now unfortunately, there's no date code written on this upgrade note, which is a little bit unusual. However, we're looking at a PDF, so I thought, okay, let's go and look at the properties of this PDF in Adobe. And here it is here, the description here, the title of it. It was authored by Helen. Thank you very much, Helen. And it was created on the 25th of February 2003. So did B16 come out roundabout then? Who knows? So a little bit about the actual shield here that I took off earlier. It serves two purposes. The first purpose is when it's in place here, you can see that you've got the exhaust fan at the back here, and what it does is it draws air in through a vent at this side here. If I just lift it up, you can see the vent there, and it draws air in across those TO220 packages here, round the corner across these ones as well, and then drawn out through the exhaust fan at the back. Now the shield comes right down onto the circuit board here, and the reason for that is to stop any airflow across the analog circuitry there. You don't want that airflow across there. The second purpose of the cover is actually it's conductive. Let's take a look. On any 2 points of the inside there, you can see I've got 1.3 ohms. It's conductive paint completely over the inside, and also down onto this boss here that secures it to the PCB. And it's no accident that the actual PCB has exposed copper where that mates up with the boss. It's not earthed, it's actually tied to the low input on the front of the meter. Therefore, this cover is held at 0 volts potential. Okay, let's tear it down, let's get the circuit boards out. Wow, basically you have to take the whole thing apart. Remove the transformer, remove guides, remove the push rods for all the buttons in the front, remove the display assembly here. You basically have to tear it completely apart to get the circuit boards out. And even then I'm not quite finished, because on the back of the analog board it's got what looks like another shield. Hopefully that's just push on by the looks of things. It's got a couple of rubber stoppers there at either end, so looks like that just pops off, and hopefully it won't be too long before I put it back together again, because with something like this you forget how it comes apart sometimes. But plenty of photographs, and I've got the circuit boards out. So yeah, the digital board's out as well, and everything looks brand new. It looks brilliant. Digital board's out because I do need to replace this large electrolytic capacitor here. I'm just taking no chances, I'm just replacing everything, and there's a few other electrolytics dotted around as well. So, and I've actually received all the capacitors and the LM339s that I need, even the fuse holders here, the new ones, I can replace them as well. So I'll get going with that, and I'll start replacing the caps, and then I'll come back when we're ready to reassemble, or if I find anything in between times. And here's the back of the analog board, and looking at the back of the electrolytics along here, I don't think they've ever been replaced, so they're probably the original capacitors. But there is one thing I've noticed on the back here. Let's take a look. There is some discoloration here. Looks like the remnants of burning flux or the heat off a soldering iron here, which has kind of found its way onto R303 there, and it looks like there's a component here that's been removed. And yeah, so taking a look at the other side of the board, W102 isn't on the board, and it looks like the holes have just been filled in. It looks very much like somebody's desoldered a component from the top side because they didn't bother taking out the board and didn't get access to the back to desolder it properly. Hence all that scorch marks on the back, or smoke marks on the back there. And a little bit of digging, W102 is not fitted. I just looked at the Signal Paths video of their repair of the 2001, and it's very, very clear this component is not fitted. But I will tidy it up anyway. I will clean that up and resolder R303 because it don't look like it's in the prettiest of states. First things first though, let's get rid of that LM339. There we go, that's it removed. Now I'll tidy up the tracks and see what sort of damage we've got, if any. And a cleanup. Wow, look at the colour of that flux. Okay, with the digital board disassembled, something caught my eye, and that is this 5-volt regulator here is completely discoloured. That's not looking good. So let's put the meter on it and see what we've got. I think that's the output. Wow, dead short. Oops. And the input, 8 ohms. That's not looking good. That's not looking good at all. So I'm going to remove that from the board. I'll not put a new one in just yet. I'll remove it from the board and do some more measuring. Okay, there's the 5-volt regulator removed. So let's go across it first. On the output, it's not shorted. Input's 8 ohms, so that's definitely too low. That's the ground. And on the circuit board, go across the output, we've still got a dead short, but the input's up. Yeah, it's charging the capacitor, so that's fine. So we've got a dead short on the digital board somewhere. Oops. Let's dig a bit deeper. Well, this repair is going to turn into a cracker, I think. I think we've got problems, big problems with the digital board. Brilliant. So I removed the tantalum capacitor that's across the output of the 5-volt regulator, and it's fine, it's not dead short. Okay, so we've got a short circuit across the 5-volt rail. I've been doing some digging around. I've been putting my ohmmeter in 6.5 digit mode, as high a resolution as I can possibly get, and I've been measuring across the various ICs and the various points, the various components, trying to narrow down which section of the board had the lowest resistance. I've done that in a video before, so I'm not going to do it again here. And I kind of got two areas, I think. It was real confusing. I was getting low readouts at both ends of the board, maybe not so much in the middle or around a certain area, so it kind of got me to thinking there was a short circuit in two areas. So I narrowed it down to one of them anyway. There's two diodes here, CR618 and CR617, and those are a couple of protection diodes there, which are absolutely dead short, both of them. And basically, as far as I can see, there's a digital line coming in via this connector here that goes away off to this IC over here, and those were dead short. So I cleared that, And my dead short, which was down about 0.06 of an ohm, is now 1 ohm. So it took a definite jump north. So there's still a short circuit somewhere, and I really wasn't getting anywhere with the meter. It was kind of giving inconsistent results. So I've resorted to a different way of doing it, and that is to put 5 volts into the board where the regulator is, and use the constant current mode of my power supply, starting at basically 0 milliamps, which when you first switch on it's going to pull the 5 volts right down obviously, and start going up in steps of 100 milliamps until I could see on the thermal camera whereabout I was getting the hotspots. Now I was getting 2 hotspots. The CPU itself, fair enough, it's a CPU, it's probably going to run hot, but also this IC over here, and it just so happens that this IC here is the line that those 2 diodes are connected across. So I'm kind of surmising at this point in time we've got a rather high voltage coming in on that digital I/O line. It basically blew the 2 diodes and possibly blown this IC here as well. Now I haven't run it at too high a current, but I can clearly see on the thermal camera that everything's stone cold apart from the CPU and this IC here. So just to demonstrate, here's a thermal camera, and you can see the CPU down here. It's got a hotspot. There is some other hotspots like this one over here. That's a reflection. That's just the copper pad that's shining there, and it gives a false impression of a high temperature on the thermal camera. But if you look across here, actually we've got 2 hotspots. We've got this IC here, the one I was talking about, and we may have this one here as well. But everything else, if we just scan across the board, all those hot spots there, that's just reflections. Tops of the capacitors there. And the crystal down here. So yeah, we've got 2 hot spots. So I think I will replace those 2 anyway. I'm not going to replace the CPU at the moment, because it's, you know, they do run warm. High performance processors like these, they can run warm. So, but these 2 here, not too sure what they are yet. Let me look up the datasheet and come back. So we're getting somewhere. I've removed this UDN 2596. It's just a driver chip, a buffer driver. It interface with the I/O in the back of the unit, I believe. And so with the chip removed, I will be putting a socket on there. And you know, it pays to have a stock of DIP IC sockets. Yeah, I think I've got a problem. And now my resistance across the 5 volt supply, it's creeping up. We were at 1 ohm, and now we're at just under 6 ohms. So it is creeping up, and I have put 5 volt across it, current limited, and it's still drawing far too much. So I think the next one along is this TK7487. Now I can't get them anymore, but I can get a compatible chip. But I'll remove it from the board, and then we'll see what like the resistance across the 5 volt supply is like after that. Only other thing that was getting warm, as you could say, as you saw in the thermal camera, was the CPU itself. Okay, I think I've just got 1 short circuit left. I have removed the TK7487, put a socket in its place. I've removed the UDN 2596A socket there as well. And I've been going over the 5 volt supply across the remaining chips, etc. on the board. And I think I've got 1 short circuit left. And I believe it's the actual CPU itself. Now there's 2 clues for that, and that is, if I turn the board over, you can see that there are a bunch of capacitors dotted around on the back of the board. Those are the decoupling capacitors next to the various ICs and connectors. And as you can see, the CPU here actually has 4 of them because there are multiple supply pins to that CPU. There's not just the one pin. And I've gone over each one of them and narrowed down the lowest resistance across C640. Nothing else is as low. I mean, you're talking small differences, but those small differences make a difference. So with this one here being the lowest resistance on the whole board, I believe the CPU is knackered. There's another reason why I think the CPU is knackered. Let's go back over again. Okay, got my multimeter set up. If you look down here, we've got the CPU and we've got the crystal. And if I find a ground, which is actually the body of the crystal, it's grounded, it's soldered down at the back there to the circuit board. If I just use that as a ground and go into each one of the pins on the crystal, you can see that this leg here, you're talking 0.6 of a mega ohm. And if I go into this one here, 3 ohms. Now let's take a look at the circuit diagram. Here's the actual crystal with its parallel resistor there and the 2 33 picofarad capacitors in the back. And you can see it's interfaced directly to the CPU, and that 3 ohm resistance that I'm getting is on this EXTAL. That's the crystal input, or the external clock input, and there's no way that should have a 3 ohm resistance down to ground in any circumstances. If you're not using a crystal, you can actually drive that. It's CMOS compatible, that input, if you're driving the CPU from an external clock source. So there's no way it should have that resistance there. So I believe it's internally shorted. It's certainly nothing on the outside. So all in all, I think the CPU's got to come out. And by some luck, I was able to pick up a couple of new old stock CPUs there. So I've got 2 of them to replace the one on the board. So let's take it out. Now the next problem is desoldering this from the board. This is a 6-layer board, and you can see that from the legend down on the corner here. Let me zoom in on that for a look. You can see a 6 there, and very faintly a 5, a 4, 3, 2, 1, etc. Those numbers are on each one of the 6 layers. That's why it gets fainter as you read it. The 6th layer being the top layer. So we know this is a 6-layer board. And if you look on the back of the CPU, you can get a clue as to some of the other layers, or the next layer down from this bottom layer. You can see what looks like a plane here, a copper pore here, and there's probably other layers. There's probably a 5-volt layer as well, so you've got a lot of copper pores across those 6 layers. And the problem with that is, and I noticed it when I was removing some of the other ICs, like this PLCC package here, is it wasn't easy to heat up and remove the chip. It took quite a bit of work. The legs of the ICs where they go onto the board were very resistant to the heat. I had to turn up the heat just that little bit more and hold it longer on the pins. Now for a big package like this, it's not going to happen. By the time you put heat on here, by the time you get right round and back to the start again, you're going to lose heat. It's going to dissipate quite quickly into those copper pores. So how are we going to get that chip off the board easily? The answer is one of these here. Now this is a QFP 132. It's a 132 pin package. This is an adapter for my heat gun here, which sits very nicely completely over the package. The little gaps at the side here actually straddle the plastic parts of the package there, so that it goes really nice and tight down onto the top of that chip. And here we go with an alternate view. If I just put the heat gun, perfectly straddles that chip with the plastic packages sticking out either corner. So let me get going. Let's get that package off the board there and clean up the PCB and see where we are after that. There we go, and that's it off the board. And as you can see, every pin nice and intact, no pads lifted. Right, let's take a look and see where we are now. Here we go, across the 5V supply, 29.76 ohms. We're getting closer, but we've still got some problems on this board. Right, I think I've found the next problem, and that is the actual 4 MHz oscillator itself. So I'm not going to remove it from the board, I'm just going to desolder it at the supply side. Just lifting it very slightly from the board to isolate that supply pin there. It looks like an IC, it's got the same sort of pin out. Pin 2 is your ground round here, and pin 4 is your supply pin. And if I go across the supply pin now on the actual chip itself, I'm getting 84.5 ohms. So with it lifted, the actual oscillator itself has got about 85 ohms across it. And with it isolated from the board, I'm now getting about 45 ohms across the 5V supply on this board. Still too low, I think, so we need to keep going and find the next culprit. In the meantime, I'll desolder that completely from the board because I think it's gone. Okay, so I took out one more chip. There was a buffer chip, a latch down here, a 244 I think it was. I've removed it. I wasn't sure if it was causing a problem, and it wasn't. So I've actually powered the board up now again with a 5V supply, and I'm achieving 5 volts, and it's drawing about 330 milliamps as it sits. Now I'm missing quite a lot, but I thought we could go back to the thermal camera now and let's just see where we're drawing that 300 odd milliamps. So let's get the thermal camera on there, and as it auto calibrates, and I've got nothing really here standing out, so let's go along here. That's the crystal down here, so don't worry about that one. And we've got the tops of 2 capacitors here, but over here we've got a hotspot, and there looks to be 2 FETs on that board, and they are getting hot. Let's take a look at that. Okay, I've removed this little daughter board from the board and powered up the main board again. 30 milliamps at 5 volts. That's much more like it. So it looks like this on its own was drawing about 200 odd milliamps. So yep, this has also got a problem. Now what is it? Well, let's take a look at the schematic. It took me a while to find it on the schematic because none of the actual components on it are actually detailed. This is it here, known as U625. It interfaces to the actual display board, and what I think it's probably doing, it's probably producing the high voltage supply for the actual display board itself. And it's probably got a little oscillator or something like that, and then step up the voltage using this little coil here to produce that high voltage. Okay, I've reverse engineered this little board here because I don't have a schematic for it, and I really needed to work out how it was working in order to troubleshoot it. So if we go down onto my little reverse engineering drawings here, this is what I started with. I basically drew the components out as they lay out on the board. Then the red pen is just the tracks on the board. I'm interconnecting it, and then I transferred this to a small schematic. And if you look at the schematic, starting with this side over here, I think this is the final high voltage output that goes off to the display. And the reason I think that is you've got an electrolytic capacitor here. This one here, it's a 250 volt 1 microfarad electrolytic capacitor with a bleed resistor across it. It's connected to a bridge rectifier and one of the coils on the transformer, one of the output windings. So I think this is your final output here. On the other side, we've got two transistors, two NPN transistors, two diodes, etc., and a 5-volt supply coming in here on a center tap of this winding here, and either side of that winding is connected to the collector of these two transistors. I think these are switching on the primary side in order to generate a secondary side. Now I am getting some seriously low resistances across the diodes and across the transistors, so I'm going to pull the transistors to begin with, which will help isolate the diodes, and I can do a bit of measuring with the components out to make sure those transistors are okay, and also that the diodes are okay. I shouldn't need to lift the diodes to test them. And here we go, I've got the two transistors off. They're just general purpose power transistors, small ones, and between the base and the emitter 0.6 of an ohm and 160 ohms between the base and the collector on that one. So that one's gone. And a similar story here by the looks of it. Just reverse the leads. Yeah, 0.4. Yep, those two transistors are gone. So let's check the diodes on the board. 0.5 of a volt, yeah. And the other way around, nothing. And this other one, nothing. And 0.5 volt. So the two diodes are okay. So I think what's happened here is, I think the 5-volt supply obviously went haywire, and it's blown these two transistors here. So I should have something that's compatible there. They're just general purpose power transistors, so I should be able to find something in my stock that can replace them. Okay, next thing I'm going to do is put the board back together again. I've got quite a lot of parts in a box here, stuff I'd received, so I'm just going to go away off camera and repopulate the board. Some of the ICs I'll be putting back on that I'd taken off and are apparently okay, and some of them are new stock that I've managed to pick up. So I'll go away and put the board back together again. And there we go, there's the new CPU fitted, and I've fitted the new capacitors there. And well, yeah, I'm just short of a couple of parts. There's an IC over here which I'm replacing. That's the dual rail supervisor IC. I think that's probably got a problem, and I've powered it up and I'm getting a nice low current draw, so without that IC it's not really resetting the CPU, so I can't really power it up and do any kind of tests at all really. And I'm still waiting on this IC here that controls the digital I/O at the back of the meter there. So that's about as far as I'm going to go for this video. So the plan is, when those parts come in, and also when I get around to replacing the two transistors on here, I can put this high voltage generator down onto the board there, and I'm hoping that I can connect up the actual display board which interfaces on this connector here. I don't see any reason why at least I shouldn't get something on the display from the main CPU just in this state here. That's the plan anyway. Thanks for watching.